Welcome, welcome. Good morning. Okay. Welcome back. Back into it. Let's do another 4-day stretch of this. It's. The stream's working. This one. Chat. Okay. Oh. Looks like I might be talking mostly for the VOD. Alright, good morning to, looks like one of you. Welcome, welcome. I finished my tea quick in the beginning. I'm sure more will be filtering in. But we're doing unit testing today. We want to get through all these slides. And this is where the course really picks up in 2 days on June 5th, this Thursday, 8 a.m. So the start of the next lecture, 48 hours from now, is the expected deadline for task 1. And I wanted to pull up some stats for y'all, because quite a few of you have been starting it. Did take my advice and started early. So I want to get some stats on how many of y'all have finished it. So let's take a look at that. And 27. That's pretty dang good, I'd say. 27 out of 58. 58. So we're past halfway. So I'm feeling good about that. I like when y'all get ahead. It's less stress for you. It's less stress for me. I don't like seeing anybody fail, so it's nice that we're hitting that. To the rest of you who have not even started, which is most of the rest of the class, it looks like three of y'all have three of y'all have submitted without finishing the assignment. So the rest of you who haven't even made a submission yet, get started, get doing it. All right, so let's learn about what we're even doing for that, what we're talking about. So let's start unit testing. Man, why does it? And I'm going to start with a complaint. Oops, I clicked the wrong thing. So it has the ocular symbol there. It makes it look like if I open it here, it's going to open in ocular, but it does not. You have to open it here and then open it in ocular. All right, and I think everything's set. Okay, let's do this thing. Hey, I'm remembering my shortcuts. Okay, unit testing. So this is the question we want to ask ourselves the whole lecture today. How do we know if our code is correct? It's a big question that you'll be asking yourself throughout your whole career. How do you know if your code is correct? And there's never a real, just definitive answer to this either. This is something that each of you, each dev is going to figure out for themselves. Like, at what point are you comfortable with, feeling that your code is correct? How much evidence do you need that your code is correct for you to feel comfortable with it? And hopefully that amount of evidence is enough to actually have correct code. But everybody's going to have a different comfort level for how much evidence they need. So let's talk about how we're even going to assess this. How are you going to check if our code is correct? So let's kind of go through what I call our progression of testing. Go through our progression when you first start learning coding. So this would hopefully be last semester. You went through most of this progression. And the first thing you do is just submit to whatever auto-grading tool that you have for the course that you're taking for your first course. Here at UB, that's Autolab. You just submit to Autolab. If Autolab coughs up the points, you know your code's right because the professor's grader said it's right. So you don't really have to think about it too much for that first step in your evolution of testing your code. All the testing is done by somebody else. This isn't ever going to exist outside of an academic environment. So, of course, we have to wean you off of that eventually. And it started in last semester. It starts immediately. But we're going to continue that this semester and throughout the rest of your time in college. Because by the time you graduate, we have to make sure that you are not relying on Autolab at all. Like you have to be able to write code without anything sitting there saying this code is correct or this code is not correct. You need to determine that by yourself, so you can sit there, write code, and release code to your users without releasing buggy code. Nobody likes using software that's all buggy and crappy and glitches and crashes. Nobody likes using code like that. I don't want you writing code like that. And I don't want you out there in the world writing code like that, and then I have to use your code and then have it crash. Then I'm going to be real bad. I'm going to, if I ever know it's you, I'm going to send you an email say, like, what the fuck? I taught you how to do better. Why are you doing this? So Autolab's not going to exist. So the first thing that you do to actually test your code, hopefully last semester, your CS1, wherever you took it, if you took it at UB or wherever, hopefully they got you at least to this point where you're running your code. You'll say... you'll like go to office hours and there's a common interaction. You ask the TA or professor, you say, hey, is this code right? And they'll say, I don't know, run it. Run the code and look at what it does. So they get you to write a main method, you call your method, you give it an input, you print the output to the screen, and you manually verify if that is the right output. And this is where I would expect every one of you to be at, if not farther than this. This is where I would expect you all to be at this point, is at least being able to run your code and check on certain inputs, what did it output. You should be able to do that. If you can't do that, if you're still on the Autolab part, I congratulate you on getting through 115 like that, because that's tough to never even test your own code. You probably spent a lot more time on the assignments than you had to. If you're testing your own code, you get through the assignments a lot faster. And that's kind of the theme of testing, is you're going to write code faster, you're going to write better code, you're going to write it faster, you're going to spend less time tracking down bugs and debugging your code. It's just going to be a lot more pleasant experience writing code. Tests take, and what we're headed to now is unit testing. We're going to automate that process of the main method. And writing your tests, it does get a little tedious. It is work. It's, morning, Dave. It is work to write your tests and set up what we're going to talk about today. But it does pay off. It is worth it to be able to not be up till 2 in the morning chasing that bug. You can write your tests, and makes it so much easier to find your bugs. So that's what we want to talk about today. We want to automate the process of testing our code to see if it is actually correct. I'm just going to chug this tea because I don't want to be sipping it throughout the whole lecture. All right, mission 1 accomplished. Okay, so what we want to do is something called unit testing. We want to write a series of tests that are going to test our code in an automated way. What we want to do is be able to hit one button and run every single test that we wrote in a matter of milliseconds. That's what we want to be able to do. So when we write these tests, what's going to happen is we're going to write specific test cases or test inputs. We're going to call our methods on these inputs and check or assert, as we're going to see, that the method returned the correct output. That's what we want to check. And the test is going to pass if and only if all of the tests pass. If even a single test case fails, the test fails, the code fails, everything, it's wrong. It's either completely right or it's just flat out wrong. And you're used to this from 115 anyway. Like, this is how we grade code. It has to be correct on all inputs. There can't be a known input where your code is known to fail and just say, well, that's a 95, it's good enough. We can't do that in software, because if you have a known bug and you release that software to your users, like 5% of your users, or rather your users, 5% of the time, your program just crashes or does the wrong thing. We need perfect software. The software has to be right all the time. It's kind of the point of writing software. The software is only right part of the time. Well, there's a lot of reasons to write software, but one is that it's perfect. We don't have human error when we write software. So if we're introducing human error, we're saying, well, I had errors when I wrote the code, but whatever. We'll just release it anyway. Yes, companies do that. No, you should not do that. It's horrible, horrible practice. I'm sick of using shitty software. I'm tired of it. Hopefully, you're tired of it. Every time a new game comes out, it's all buggy and glitchy and stuff. Uh, just make sure it's right before they release it. And usually, not to get too sidetracked, but usually they know that those bugs are there. They just have a tight schedule. Gotta hit the release date and make that money. So they don't have time to fix all the bugs. So they do the best they can and then release it. They have very large, modern games are huge, complex pieces of software. Absolutely crazy what they can accomplish. But sometimes bugs get through when they're pushing the limits. And they got deadlines that they got to meet. If they didn't have deadlines, yeah, we'd have to wait a lot longer for the games, but they wouldn't be buggy and glitchy. Anyway, we don't want to release with known bugs ever, but yes, I know it does happen. Very, very unfortunately. Okay, I gotta move my. I'm gonna travel over to the other side of the screen here. So I usually don't put things over here. So I think this is a better spot for my face. I don't, if I'm ever in the way of the content, let me know, because, excuse me, because I sometimes forget to look at where my face is and what I'm covering up. Alright, so let's set up this scenario. You're a coder, you're on the job, and your project manager hands you a task. They say, hey, I really need this method. It's got to take an int, it's got to return an int, and it's going to return the input plus 5. Very complex task, I know. It's going to be tough. I think we're going to have to spend some time writing this code. And oh wait, here it is. Okay, we wrote the code. Just return x plus 5. Cool. We did all our Java stuff, public static, return type. The parameter has a type, all that stuff. We're returning a value with the type, all the stuff we talked about last week. Everything looks good, but how do we know it's correct? How do we know that this code is actually correct on every input? Now, the method here, let's get this out of the way. The method is ridiculously simple. We can just look at this code and know that it's correct. Like, it's just correct. We don't have to do any testing with this. It's just adding 5. And I want to use an example that's simple enough. And we're not getting bogged down on the details of the code. I don't want you getting distracted about the code that we're testing, because today is not about writing code. Today is about testing our code. So the code is super simple, so you're not distracted by the complexities of what the method's doing. It's just adding 5. It's a really, really dumb basic method you would never actually write, by the way. So how do we know it's correct, though, without looking at the code? So assume that you just have this add 5 method as a black box. You can't see the code. You just need to test this code, this method, to know that it actually does what it's supposed to do. So if you couldn't even see the code here, how would you verify that it does the right thing? How would you build confidence that it is actually adding 5 and returning that return value? So with our progressions, with what you would, or hopefully at right now, what you would do right now if I didn't talk about unit testing at all and just gave you this task, test if this method is correct, you'd probably come up with something like this, I would hope, is main method, call your method a handful of times, and then print the results to the screen. Whatever the method returns, print it to the screen. So we're going to come up with some inputs, 2, 5, and 1, and we're going to expect 7, 10, and 6 to be printed to the screen. So we run this code and we manually verify with our human eyeballs what was printed to the screen. We see 7, 10, 6, and we say, that looks good. Yeah, that looks good. 7, 10, 6, that's what I expected. That's what was printed. Looks like everything worked the way it was supposed to. But this is going to fall apart. This isn't going to serve us very well for too long. This is fine when it is such a simple method. When it's the 115 level methods where it's strictly input-output behavior, the behavior is usually just some math or string concatenation or very simple operations and very small methods and methods that don't interact with each other very often. Hopefully they got a little bit of a method calling another method in 115. I'm certain they do at UB. But you don't have too much interaction between different pieces of code. In 116, where our focus is on what happens when programs get larger, we'll have multiple files of code that are all interacting with each other to build one program that does more complex stuff. So we're going to have we're going to be getting pretty complex code, and eventually, obviously, we can't do this in a semester, but we could. You'll eventually in your career have projects with hundreds of files that all interact with each other in very complex ways. Just a lot going on in your program. And when you make a change to that code, you have this big web of files and code that's all calling each other's methods and creating objects of different classes and everything. And you make a change right in the middle of that. How do you know you didn't break anything? When you might be changing a method that's called from 20 other files of code, from 20 other methods and 20 other different classes, all calling that method, how do you know you didn't break anything in the whole pipeline? Well, you're going to go to your main methods, you're going to run every single one, you're going to print hundreds, maybe even thousands of values to the screen, and you have your big list of expected outputs, and you're going to manually verify one at a time. With your human eyeballs, you're going to check every single one of those. I'm not doing that. I don't know about y'all, but I'm not doing that. I'm not going to bother. So we want to, what we want to do is automate this. We want to take this idea of running our methods with specific inputs and checking the outputs, but we want to get our human eyeballs out of the equation. Just hit one button and let it all rip in milliseconds. That's what we want. That's our goal. So how are we going to do that? This is where unit testing comes in. That's what we want to talk about for the rest of the day today. So we're going to reorganize our code. We're going to do the same thing we did in the main method, except we're going to reorganize it in the form of unit testing. So let's check out our first unit test. It's the same inputs, the same expected outputs as we had before, but structured as a unit test. So let's do this. So this is a separate file. It's in the directory week 2 in the file addtest.java. So this is a separate file calling this code. And let's go through this one part at a time. Let's break it down and talk about what all this is in the unit testing. So first, unit testing is an external library. This is our first external library that we're seeing. And what that means is it's a library, it's separate code, separate Java classes that are not pre-installed with Java. When you download the JDK, this unit testing library called JUnit that we're using is not part of Java itself. It's another group of developers who wrote this library and made it publicly available to use with Java, but it is not pre-packaged with Java. So we have to go to the internet, download this library, link it to our project, add it to IntelliJ, to our project and everything, and then we can start importing and using the classes in that library. Which used to be a big pain, back in the day, one of those things. It used to be a pain actually doing that. Now it's almost too easy for an educational environment because you don't really learn how this works. But it's in your, when you clone the repo, you'll notice a file called pom.xml. And what we're using that for, that's a file that's going to be read by a program called Maven. Maven's going to see that pom.xml. And the pom.xml is listing all of our external dependencies, which includes JUnit. So Maven sees that pom.xml, sees that we have JUnit as a dependency, and then it goes to the internet, downloads it, and links it to our project for us. And it all just happens magically in the background. It's one of the things where when you clone the repo, that's one of the first things that happens. One of the progress bars on the bottom of the screen is Maven running and downloading JUnit for you. So by the time you get to actually the point of actually writing unit tests, this should just already be resolved. If you ever get errors here, that means something went wrong with that Maven pom.xml, that whole process. Usually Usually what that means, whenever I've ever seen that, it's almost always, I have to say almost because there are a few really strange cases. It's almost always that a student did not clone the repo using Git. They didn't go clone from version control and paste the link and everything in IntelliJ. What they did, I didn't demo that last week, did I? In this lecture. What they did instead, or did I? I forget. If there are questions on that, I can just demo it today. If anybody asks, so if I didn't demo that, just ask, and I'll demo it. If you're watching the VOD, you missed your chance to ask. Or come to office hours. That's what I was saying. If there are ever any errors, that means something went wrong with that whole process. And what that usually means is a student, instead of cloning the repo, what they did is went to GitHub and just copied the files manually one at a time. And they didn't copy the pom.xml because it's not Java code. I don't need that, right? Or they did copy it, but Maven didn't see that. When you copy and paste like that, sometimes Maven's going to miss that. If you clone it, Maven's going to do a scan and check for stuff like that. But if you copy and paste it, it doesn't always hit. It doesn't always see that. So if you do have that issue, make sure your pom.xml is there. Right-click on the pom.xml and say Add as Maven Project. It'll get rid of those errors. But I rarely see those errors. There's very few students who are doing the manual cut and paste these days that I see. So there's a lot going on with that to get this line right here, just this import statement to work. But it's just so automatic these days that it's just not a big deal. It used to be a whole thing, a whole setup, big post on Piazza and all kinds of stuff to be able to get students to set up their external libraries. It's so easy these days. In most languages, it's pretty easy these days. All right, and then the next thing, I just want to highlight this one because we have different syntax. If the syntax is tripping you up, don't sweat it too much. It's not something you fully need to understand, but I do want to explain this. Another like tips and tricks, like again, referring to the syllabus, I expect you to want to learn about computer science. Kind of expect you to want to see cool things. So I imported this in the way, this is the way they do it in all their documentations, where is one reason I did this. But also I left it this way because I do like the way they import here. So what this is statically importing a static method. So where most of our every import statement we've seen so far is importing an entire class. Actually, test is an annotation, but it's a class that defines the annotation. This one is a static import, meaning that we're importing one single static method. So we're importing from the package org.junit from the assert class. This is the capitalized one, so this one is the class. And then from that class, we're importing the assert true method. And since we're importing a static method, we use the keyword static right here. So what this does is lets us call assert true, just like with syntax that makes it look like a function. We haven't really talked about the difference yet, but with this syntax where we just call it, just straight up. As opposed to what we're doing on the other side here, add or dot add 5, this is usually how we call a static method. We invoke the class itself, the class for that method, and then dot, then the method that we're calling, the static method that we're calling. So we're calling add5 through the adder class, so we do adder.add5. And adder, for this example, these are in the same package. Any two classes that are in the same package do not have to import each other. All the classes in the same package are automatically imported in Java. So I don't have to import adder, but I do have to call the method through the class. I could do a static import and import the add5 method the same way I'm doing this right here, and then I would just have to do add5 without adder dot each time. So for problem set, you're doing problem set, you're importing your problem set because the testing and the problem set are in two different packages. You're importing problem set and then doing problem set dot average, problem set dot sum of digits, problem set dot best key. So you're calling the methods through the class. On your testing for task 1, you can also do a static import. Since all three of those methods are static, you could statically import them and then not have to do problem set dot every single time. You can use that same Same syntax as here. For my money, for what it's worth, I like doing regular imports here, so I know that add5 is coming from the adder class. I like to have that reminder every time. But assert true, I know is coming from JUnit. It's not coming from anywhere else. I'm not importing asserts from all kinds of different places. They're all coming from JUnit, so I like static imports here. But this, sometimes I'll forget what class I'm testing a method from, so I do like the adder here. Okay. And now that we imported these things, we get to use them. And test that we imported, as mentioned, was an annotation. I'm just going to be covering up some of this. It says annotate with @test behind my head. Is this test annotation is going to tell JUnit, Java, IntelliJ, however you want to look at it, the JVM, that the following method is a test. So we're going to write a test. That's the next thing we're about to do. And we use this @test annotation to say, hey, the next thing I write, this is going to be a test. So treat it as a test. And when we run this code, we're going to, what JUnit's going to do is look through our class for every single method that's annotated with the test annotation and run those, treat those as unit tests, as our testing methods. The reason for this is we can have other methods in our testing class that are not themselves tests, some testing helper methods, and we just won't annotate those with the test annotation to indicate that, hey, JUnit, you should ignore these ones because these are just my helper methods. So the test annotation, don't forget it. It's a really simple mistake to make. A lot of you will do it. Hell, I do it. I forget it from time to time still. But don't forget your test annotation. If you forget this annotation, your tests, all your beautiful tests that you wrote just simply won't run. They won't be ran as tests. So just don't forget your test annotation on all your test methods. Don't forget your test annotation. Thank you, Slide. Slide's got my back. Okay, and then the method itself. So all your tests are going to be public void methods. Notice that these are not static methods. I'm not diving into the difference right now. Just know that JUnit needs non-static methods. Your test methods for JUnit are non-static. So public void, I believe if you put static here, at the very least your tests are going to be broken. But there will be some form of errors or your tests won't run. I don't know. I haven't put static there to know. Let's do that real quick. Let's hop to IntelliJ. Let's do a little bit of, just a tiny bit of IntelliJ here. If I put static here, it should just be an error. Yeah. Method test add5 annotated with @test should be non-static. So it's not a mistake you can make. It's not something you have to memorize. Just, but just for what it's worth, these are non-static. We can close these old ones. Oh, I didn't even talk about what the slide's talking about. And then the method name, so public void, so no return type, no parameters. You can't have parameters in your tests either. And then the method name is going to be your test name. So when these tests are ran, you're going to get some output in IntelliJ. Since you know what, should have done that while we were there. When you run your tests, so I have this class add test, which has more tests. We're going to talk about the rest of these here. But when I run this class, I'm going to get this output over here. I'm going to get each test method, like test add5. I'm going to get the result of that test. All these tests pass with the green check mark, so we can see what happened with all these tests. So my recommendation is to give your tests meaningful names, because it's going to make it a lot easier to read that output if you have meaningful names. It's going to be easier to read the output so you know which tests correlates to which one. Yeah, a lot of you are going to name your test 1, test 2, test 3, test 4. I'm not going to stop you, but I do recommend having meaningful names here, so you don't have to keep wondering, wait, which one was test 3? What was I testing there? And these are also going to be used in the Autolab output. So to make the Autolab output easier to read and easier to understand without having to go back to your tests and take double checking which test is which, give them meaningful names, makes your Autolab output just that much simpler to read. So meaningful test names, highly recommended. And then finally, our test cases. We're finally ready to actually test our code. Just like last week, it took a while to get through all the boilerplate stuff in Java just to get to the point where we can write some code. But here we are. We made it. So now we get to write our test cases. So this test class has one test that has 3 test cases. I'll try to be consistent with that terminology. I sometimes say test suite instead of test class. If I say test suite, I mean the whole test class itself. In Scala, we used to call them test suites, and it's kind of stuck in my brain still. But test class can have multiple tests, and each test has multiple test cases. So I have 3 test cases here that I'm testing my method on, which are single input-output behaviors. On the input 2, I expect 7. On input 5, I expect 10. On input 1, I expect 6. And for each test case, I'm going to assert what the outcome should be. This is the critical part here. This is the whole point of testing, is to add our asserts. So I'm using this assert true method that we statically imported from the assert class. And I'm calling this method to assert a value that I expect to be true. So I expect this Boolean expression to be true. Adder.add5 of 2 should resolve to 7. That's what I expect. So this result should equal 7. So this Boolean expression, I expect this to resolve to true. And I'm going to assert that it resolves to true. This is how we set up a test case in JUnit. So assert true is going to check, does this Boolean expression resolve to true? If it does, we're good. Nothing else to do. Just move on to the next line. If it resolves to false, the only other option, if it resolves to false, then the test case fails, which means the test fails, which means the test class fails, which means the code is incorrect. Or sometimes the testing is incorrect, depending on where you're at. But something's wrong. Everything shuts down when this happens. If an assert fails, the entire test shuts down and says, your code, you got a bug, you got something to fix, go fix your code, and then come back, run this again, and then we'll see how it goes. So that's the strictness that we have with testing, and for good reason. It should be this way. I don't want to release buggy code. I don't want to write buggy code. I want every one of my test cases passing before I release code. So once you have one test case failing, the rest of the test cases aren't even executed. The whole thing shuts down and then says, all right, we're done here. The code's wrong. Here's what you got to go to fix. And this is what your debug cycle becomes when you have tests. First, I recommend writing tests before the code. It's kind of a losing battle. I just can't get students to do it. So I'll recommend it there. I recommended it, but so few of y'all do it. Or rather, what I like to tell myself is some of y'all are writing your tests before your code, but I never have to see you because you just effectively write really good code and you never have to come to office hours because you just wrote your test first and it made it way easier to actually write your code. But the students I see in office hours, I should specify. Students I see in office hours who are struggling never write their test before their code. So maybe give it a try. That's my pitch. I'll leave it at that. I've been unable to get the struggling students to do this, but it is what it is. So your debug cycle becomes write your tests. So you have a really nice set of test cases and your tests well organized in your test class. Write a whole bunch of tests for the method that you're going to write, and then write your code after your tests. So when you write your code and you think, oh yeah, okay, I wrote this beautiful method, I think it's great, everything's going great, you don't just have to say, yeah, I think it's right. You can run your tests and verify if it's right, because you already have a really good set of tests. You're going to run those tests. If your tests pass, hey, you wrote great code, congratulations. If a test fails, then we start our debug cycle. Test case fails. Now we know, say it fails on 5 equals 10. Input 5, expected 10. Then what we know is the exact test case that failed. So we can go through our code and say, okay, on input 5, what does my code do? I expect it to return 10, but it doesn't because the test case failed. So where did I go wrong? And you can use that to start figuring out where your bug is on a very specific input. It makes it a lot easier to figure out what went wrong with that code. And then if you can't just spot it or right away, sometimes I'll just dive to this right away, is you can run my favorite thing and hopefully eventually your favorite thing, the debugger, which I'll get examples in whenever I can. In the summer, this is one of the things that does get condensed a bit, but running the debugger. The debugger is a tool in IntelliJ that's going to run your code one line at a time and show you everything that's happening in memory. So what you can do is run the debugger and step through your code one line at a time and verify it every single step. Is it doing what I expect it to be doing? It's an immensely valuable tool. I don't know how I would write any code without it. I don't know how I ever wrote code before I knew about the debugger and knew how to use it. It's a tremendously valuable tool. If you embrace test-driven development, write your tests and then your code and the debugger, you're going to fly through computer. Maybe not fly through. Computer science is still tough. But you're going to make computer science a lot easier than it would be without those things. Whenever you hear students say, oh man, I was up till 5 in the morning working on this assignment, I spent 50, 60 hours on this one programming assignment. Whenever you hear students saying that, ask them, your peers saying that, ask them, did you use the debugger and did you write test cases? Especially in the upper level classes where your testing isn't required. It's going to be required in 116 because you're still learning it. But in the upper level classes, when testing isn't required and you hear your friend complaining about stuff like that, ask them if they wrote any tests. The answer is probably going to be no. Sometimes it's yes, but then if you look at their tests are absolute garbage. I guarantee they don't have good tests and they never touch the debugger. Because the students who do that don't complain about staying up till 2 in the morning doing the assignments. They just do the assignments effectively. So if you don't want to be one of those people who's constantly pulling all-nighters and everything, do these things, please, please, please. If more students did this, computer science would not have the reputation of being so as hard as it is. It still have a reputation of being hard. Don't get me wrong. Computer science is just hard. Programming is just hard. But it doesn't have to be as hard as people make it if they actually take this advice. But for some of y'all, it's a losing battle. Some of y'all do take it to heart, but for some of y'all, it's a losing battle. By the time I get see students again, I'll see students in 116. I see y'all in 116, and teach you unit testing. By the time I see those same students again in CSE112, very few of them are actually testing their code, which, I don't know, it's upsetting, but because then I have to see them struggle on assignments that are supposed to be pretty straightforward, like even the basic intro assignment in 312. I see them struggling. I'm like, where's your testing? Where's your debugger? Oh, I thought we don't have to do that anymore. Like, no, you missed the whole point. Anyway, that's my pitch. I gave another pitch. I said I wouldn't sell it too much, but okay. So now notice there's one caveat to this I just want to point out, is that so please do your testing. I'll stop. But one kind of caveat to this is I said every single Java program starts with a main method. And every time we do a memory trace, I make a big deal of it. Every Java program says the dawn of time has always started with a main method. So let's put our main stack frame on here. But you just saw me run a unit test. It doesn't have a main method, but I was able to just click a run button and let it go, let it rip. So what the hell's going on here? So there is a main method for this program. It's just invisible to us. In IntelliJ, it gives us these convenient run buttons because IntelliJ understands what JUnit is and how to set up JUnit. But to actually run JUnit, we're running a class in the JUnit library, the test runner, which has a main method. We run that method, and then that method invokes our method, our class. It actually creates an object of our class type and then starts calling our non-static methods through that object. All that stuff happens behind the scenes, but trust me, there is a main method. It's just not in our code. It's in the JUnit library where that main method is, and we can verify that. Let's do a little bit of IntelliJ. I'll give you a brief taste of the debugger. So with the debugger, I'm going to set what's called a breakpoint. And then instead of running, I'm going to click the debug button. It's going to run my code until it hits a breakpoint, and then it's going to stop. It's going to stop all execution and show me everything that's happening in memory. I picked a bad breakpoint because there's nothing happening in memory right now. It's just the main method. Oh, actually, I do need to resize some things here. And close this. Can I get my... I'll mess with that later. So I can see my stack frame and nothing interesting in the stack frame. Actually, let's step into once. So add 5, I have an add 5 stack frame, and I can see my parameter 5 or x with the value 5. So it's showing me all the information that we'll have in our memory traces, in our quizzes. It gives us all the same information. We have the stack, all our stack frames here, and if I click on a stack frame, I can see all the values that are inside that stack frame. And if we had any heap values, we would be able to see those values. Well, let's just do it since I'm here. I'm going to set a breakpoint. I'm going to run this in the debugger. And I can see my list. Whenever you see this @ symbol, @ and then some number, that means this variable, my list, stores a reference to an object on the heap. And if I click this arrow, it'll take me over to the heap and show me all the values that are in that array list. So 4, 5, 6, 7, 4, 5, 6, 7. I can see everything that's in my array list. And then when we have our, oh, I commented it all out. When we have our method call, no, don't have a method call here. Why do I have this all commented out? It's because that's the wrong one. I didn't mean to go on this much of a tangent. So same thing, we have @ some number that's an object on the heap. 10, 9, 8, 7 on this one, so set up a little bit differently. And then when I have this assignment by reference, I can verify that R1 and R2 are both references to the array list @ 938. And you can read this @ just like our OXs in the stack traces. Is the same idea here. This is a number that refers to a specific object on the heap. So I can verify that R1 and R2 both refer to the same array list, this one @ 938. And they do have all the same values, but there's only one array list that's being referred to by both of these variables. We can verify all that, everything about our memory diagrams, we can verify using the debugger. And of course, we can also just debug our code. So let's get back to the debugger on our test. So on our test, we have add 5, all our debugger stuff. That's all I'll talk about with the debugger today. There might be time, there probably won't be time at the end. It's the frames. There we go. And then, so we have our 2 stack frames on the stack. That's what we expect. But if we show all the hidden stack frames, we can see a whole mess of other stuff going on. There's a whole bunch of stack frames on the stack right now. If we go all the way down to the bottom, we can get to this JUnit starter, and this is a main method, which, do I not have sources? Oh no. Too many sources and documentation. Downloading. And we see all kinds of stuff in these stack frames. Oh. Well, maybe that's the first feature that I have in Ultimate that that community doesn't do. Anyway, it is a main method, stack frame. I was hoping to jump to the code for that, but whatever. We gotta get back to some slides. But there is a main method. We can see that it is being executed right here. We're on line 55 of the main method in the JUnit starter class. That's what's actually running in the common IntelliJ RT JUnit package. So IntelliJ is invoking the runner, which is invoking the JUnit. Oh, there we go, because we don't have the IntelliJ sources. Which is running the JUnit runner. A whole bunch of stuff happening behind the scenes, all to get to our little test that makes sure we're adding 5 correctly. But all that stuff is happening, so there is a main method. It does exist. It is a real thing. It's just nothing that we really have to concern ourselves about. I just want to show you, verify that it does, in fact, exist. Okay, and then, oh my goodness, time is not with me today. I gotta stop going on little tangents about testing and stuff. Okay, so the question I have for you, going back to our question at the top of lecture, is how do you know your code is correct? We kind of transformed that question into this one. Is this enough testing? So if my test passes on these 3 inputs, am I comfortable with that? Let's say that I can't see, that this is a black box, that I can't actually see the code, or maybe I just don't feel like reading it, I don't know. But if I can't see the code, if I'm just told, hey, there's this method that exists called add5, this is the behavior it's supposed to have, and it passes these tests, how confident are you that it will always return the right output on every single input? So if we have any method, any implementation of add5 that passes these 3 test cases, are we sure that it's correct? Are we sure that method's actually right? And this is where it's going to be up to every dev, like how much testing are you going to write? How much testing will you write? In 116, it's required. Like IntelliJ, Autolab is going to force you to get to a certain point. But after that, once you don't have Autolab testing your tests, this is something you're going to have to decide for yourself. How much testing do you need to see before you're sure that your code is correct and that you're not releasing bugs to the public? And whatever your answer is, I really hope that you look at this test and say, I don't know what enough is, I'm still figuring it out, but that one is not enough. This is not enough testing. This is horrible testing because someone's going to write an implementation of add5 that's going to look like this, because sometimes some people like to get too smart for their own good. They're going to do some wacky bullcrap like this. They're going to take the absolute value of x and then add 5 because I don't know why somebody would do this, but they might. You might have some intern on the team who's like, "Oh, I'm gonna do this wacky crap," and then this code is wrong. This implementation of add5 is wrong, but it passes our tests. Our tests on all 3 of these test cases that we have, it passes. So this testing is no good because we have a really crap method here and it passes it. So let's take care of this. Let's add some more testing. What we had already, I would call the common test cases. We have our common test cases that are just like the test cases everybody's going to think of. If you ask anybody to write tests for this method, 2, 5, and 1, those are, that flavor, these small positive integers, those are going to be the first test cases everybody comes up with, hopefully at least. I mean, maybe somebody will jump right to the edge cases. Once you're working with this for a while, you might start jumping right to the edge cases. But everybody's going to think of these ones. So let's add what I'll call some uncommon test cases. These are the negative numbers, the ones that not everybody's going to think of right away. When you take the SAT, this is like one of the big things that they get you to think about is, okay, there's positive numbers, there's also negative numbers. Those things do exist. And a lot of the questions are designed to kind of trip you up if you're not thinking about negative numbers. We want to think about these negative numbers. So let's write some test cases for the negatives, and then run this test again, and we can get rid of that crappy solution that takes the absolute value. It's going to fail all of these test cases. It's going to get completely wrong answers. And this is allowed, so this is why we have the test annotation. We can have multiple test methods in the same test class. So we have two tests, test add 5 and test add 5 with negatives. So we annotate them both with the test annotation to tell JUnit, hey, I have two methods full of test cases. Make sure you run them both. And now if test add 5 passes, but test add 5 with negatives fails, that gives me more information than I would have if I put all of these test cases in a single test method. So how to organize your tests is up to you as well, but I do recommend organizing them in some meaningful fashion. Don't just throw all your test cases in one method. Sometimes that's okay. Like for the problem set, whatever, it's fine. There's only so many ways you can test the average method. You can put all those tests in one method. But as we get to the more complex testing, separating them into multiple test methods is going to be beneficial. So now these tests pass on our correct solution here, but fail this completely incorrect solution. And this is how the testing is going to work in IntelliJ. And I keep saying IntelliJ for that. In Autolab. This is how the testing works in Autolab. What the Autolab feedback is going to say is you don't have a test for this feature or this feature, but you passed on a correct solution. What's happening is we're taking your test that you submit, running it on a known correct solution, and making sure that all of your tests pass the correct solution. Because it's a correct solution, your test better pass the correct solution, which is one of the big things. If my correct solution returns dog and you're asserting cat, we talked about that last time. And then we're going to run your tests on a series of incorrect solutions with known bugs in them, and it's up to your test to identify those bugs and make sure your tests are rejecting those solutions. And if you pass one of those solutions, the feedback is going to say you don't have test cases for this bug because we gave you code with that bug and your test cases said, yeah, it's good. That's fine. So now we are passing the correct solution and failing the incorrect solution. This is what we want. This is great. Except we're not quite there. There's one big test case that we really need for to really gain some confidence that our code is correct. So let's say somebody comes along, takes our very simple, elegant add 5 method that just adds 5, and they rewrite it like this. They say, well, let's see. We're going to add 5 to this. That means we've got 3 different situations. We can either have a positive number, a negative number, or something else. And if we hit the else, I can't think of anything that's not positive or negative, so we're just going to return x in that case. If it's negative, okay, they didn't like my absolute value method. That only works with positives. So if I have a negative number, I'm going to take the negation of that absolute value and then add 5. Somebody's going to way overthink this. And this does happen. Maybe not with this exact method. It'll be slightly more complex than adding 5. But people do this. Developers do this. Like, they actually do this. They way over-engineer. I'm guilty of this sometimes. Way over-engineer, way overcomplicate even some simple tasks. And the actual situation where this can come up, I know, because even though I have this toy example of, just adding 5, writing tests for add 5, it seems silly. But having tests for even your very simple methods can be beneficial when you're out there in the real world working with a team collectively on a project. Because the situation that can happen and does happen is you write your method, it's super simple, can't possibly go wrong. It just adds 5. Why do I gotta write tests for that? That's silly. And then later on down the road, you have a bunch of meetings that say, okay, the performance of our code just isn't there. We need to speed things up. We need our code to be more efficient, and it's just got to run faster. It's just too slow. So somebody's going to come along And what they might do is look at that add 5 method. They say add 5, that's a slow operation. We're going to speed this thing up. We're going to optimize the crap out of this method. And somebody's going to come along and rewrite it like this, and they're going to say, I read some research paper that says if you do it this way, it's supposed to be 0.3% faster. Trust me, it's better. It's way better this way. Or even worse these days, ChatGPT told me, I told it to speed up the method, and this is what it gave me, so I pasted it here. That's what your interns are going to be doing now. Hopefully that's not you guys, but that's what the interns are going to be doing these days. ChatGPT said it's faster. And they're going to come up with this garbage. They're going to paste it from their AI assistants, and it's just absolute trash code, which is way slower than just adding 5 in this case. But somebody's going to be convinced that it's better. And they're going to push this code to the project. It's going to be all buggy. Everything's going to be broken. And it's going to be a long day for everybody. Unless you have your test cases. If you have test cases, because this one passes all your tests. It says, the intern's going to say, well, it passes your tests. I ran your tests, so it must be right. But this passes all of those tests. So the big rewrite, and that's what you should have in mind out there in the real world, is you're not always writing tests for your code. You're writing tests for any future implementation of that code. When somebody that's too smart for their own good comes in and rewrites that code, you want to make sure those tests are going to make sure the rewrite is still correct. So that's the level of testing that you need to have in mind is, yeah, I say if you can't see the code, well, we can see the code right here, and you're always going to be able to see the code. But not really, because you're not going to see any future implementations of that method. Unless you can see the future, in that case, you're probably not writing code. You're probably buying lottery tickets and stuff like that. So if you can't see the future, you don't know what this method is going to look like 5-10 months, I'll say. Down the road, you don't know what the implementation is going to look like when somebody comes in and rewrites it on you. So you want to write tests for any implementation. So let's add our last test case here, our edge case. We always want to think of the edge cases as well. We don't want to miss that in our testing. And on this one, the edge case is 0. Commonly, any of these inputs for numeric values, 0. For strings, empty string. For array list, an empty array list. For hash map, an empty hash map. All these inputs are ones that we want to think about. Make sure that on those special cases, those edge cases, that our code is still doing the right thing. These are often cases where in our code we need a separate conditional. We need to say if this is the case, if the array list is empty, if the hash map is empty. We see this right from task 1, average. What happens if the array list is empty? It's something that's going to need a conditional. If the array list is empty, return 0. You want to make sure you have a test case for that edge case where you're giving it an empty array list and asserting that it returns 0, because it's going to be special code to handle the edge case. You want to make sure you have full test, what we call test coverage, where you're testing every piece of code in the method that you're testing. And that's a common thing that in rewrites, the edge cases might be missed. You have somebody who's just vibe coding and gets the common cases correct, but ChatGPT isn't getting these edge cases all the time, at least. So you want to make sure you have your test cases for the edge cases, so that that crappy intern you hired, make sure they don't get that code into production for the end user, because you have a good test suite that's going to catch all of that stuff. Okay, and when all else fails, and especially if you're submitting to Autolab and you're like, I have no idea why Autolab doesn't like my tests, all else fails, just write lots of tests. Yeah, more tests ain't going to hurt anything. So if you're not sure, just write more tests. So if you're asking yourself that question, is this enough testing, especially out there in the real world when you don't have Autolab giving you a more definitive answer, which even Autolab, like the bar isn't too high in Autolab. Autolab is going to pass a lot of crappy testing that wouldn't really be sufficient out there in the real world. So when you're unsure, is this enough testing? Am I confident this method's right? Just add more tests. More testing is always better. And with more tests, a good variety of tests goes a lot longer than just strictly more tests. What I'll see students do fairly often is they'll have like these 5 test cases, just the positive integers, and Autolab will say, you need more testing, you need more testing. They'll go to office hours, and myself, the TAs, we're going to say, you need more testing. They'll post on Piazza, and we're going to say, you need more testing. So, okay, I need more testing. I got it. So they're going to add some test cases, and they're going to add 3 as an input, 4, 6, 7, 8, 11, 12, 35, 64. They're going to add all kinds of test cases. And they'll be like, look, I got more testing now. And I've seen students with 20, 30, well, not quite 100, but 20, 30, 40 test cases, and they're of that flavor where every single test case is testing the same exact, not the same exact thing, but pretty much the same thing. They'll have 40 positive integers, and they won't at any point think of, hey, maybe I should give this a negative number. Maybe I should give this 0. So it's not just more testing, but more variety in your testing. For like the average method, for example, if you have an empty array list, an array list of size 1, and an array list of size 10, like just those 3 test cases, you're going to be golden. You're going to be doing great with that one. But if you have, I've seen students with like 5 test cases for the average method where every single one of them is exactly 3 doubles, array list of size 3. Maybe they'll have their edge case because that one's given in the handout. They'll have their edge case of empty array lists and then 3 that all have 3 values, and sometimes all of their test cases, the result is always a whole number, so they're not catching, anything that's doing unnecessary rounding or anything. And all their test cases are testing basically the same exact thing, the same exact functionality. Instead of giving a nice variety, given negative numbers and return values that are like repeating number, repeating decimal, and things like that. We just want to test all those things. So, results where the average is 0. I don't even think I checked for that one in Autolab, but test case where the result is 0, I would want to see in the real world. An array list with positive 5 and negative 5, things like that. So lots of tests, lots of variety of testing. If you test with a lot of variety in your test cases, you're never going to be that student with issues where I submitted to Autolab doesn't like my test, and I don't know why. Just please, I beg of you, not beg, I don't want to beg, but I urge you for your own good, is when you write tests, just sit down and write. This is going to sound silly, but just sit down and write good tests. A lot of students spend way more time than they have to on this class, partly because they'll write crappy tests or sometimes no tests, submit to Autolab, see what Autolab says, and then try to reverse engineer the output in Autolab to figure out what tests to write. And then they write tests specifically for the Autolab output. Don't do that. That's a horrible way to waste your time. When you write tests, sit down and just write good tests. Write good tests. Pretend that you're out there in industry right now and not taking a course, and just sit down and write tests that would satisfy you. Like, what tests would you need to see to be able to convince yourself that that code must actually be correct? Write that really nice set of tests and then submit to Autolab. And most times Autolab is just going to be like, oh yeah, that's good. We're good here. But in those rare cases where Autolab's like, oh no, there's still this feature that you missed, then think about that feature. Maybe do a little reverse engineering. Hopefully the feature name should act as a hint. That's the intent, is that it's a hint that says, hey, I know you sat down and write some really good test cases, but here's a feature you missed. Maybe think about that one because you missed this feature. And then you write, oh yeah, I did miss that feature. Let me write a test case for that feature. That's the intent of it. In office hours, it's not how it always goes. Too many students reverse engineering the feedback in Autolab. Some of you will do that. It's fine. I'll still help you in office hours, of course. But I'll recommend a better way. So that ideally, if you're doing that, if you're sitting down and thinking of your test cases, Ideally, you won't even need office hours. You wouldn't need me. Like the whole point is I'm teaching how to test, so you don't need me in the TAs anymore. By the time you graduate, we need you to be independent developers where you can write all this code, perfectly good code, completely by yourself. That's eventually where we need to get you. And this is one of the first steps. In 116, teaching you testing, it's one of the first steps to getting you there. We'll get you there. All right, so when you submit to Autolab, you're going to see some output. I kind of went over this a little, so I'll go a little briefer over it now, unless there are questions, of course. And when you submit, you're going to see what your test did on a correct solution. That's my known correct solution. Your tests better pass on that correct solution. If not, something's terribly wrong. Something about the spec in the handout, you're asserting something that goes against that spec. And the best key, that's the first case, the first place where I'm really testing this. I mean, you might just have legit broken test cases before then, but best key is the first time I'm really looking at this, where getting you to think about this is when there's multiple correct answers, making sure that you're accepting any correct answer. So you got to pass on a correct solution. That has to happen. If you're not passing on a correct solution, that means your test is testing the wrong thing or not accepting all the correct answers. So for example, for the average, if your average test is failing on a correct solution, then you know that your test case itself is broken. You're not asserting the actual expected value, and usually you just got to go back and check your math. You just did some math wrong or something. And then I'm going to test on a series of incorrect solutions, making sure that your tests fail all of my incorrect solutions. All my incorrect solutions have known bugs, and you should reject them all. If you don't reject a specific incorrect solution with a specific known bug, then the feedback is going to be your test did not test this feature, whatever the feature name is for that. So on the no negatives add 5 method, that doesn't handle negative numbers, that takes the absolute value first. If that was my incorrect solution, I'd probably say you don't have testing for the feature negative inputs, something like that. And that should be pretty blatant in that example. They're not always obvious in Autolab when you're doing the tasks. That example, of course, it's a simple toy example for lecture. It should hit you over the head that, oh yeah, I don't have any negative inputs in my test cases. So you make sure you have a negative input. Okay, and a few tips. Usually this spills over to the next oh man, we're 17 minutes into the next lecture time already. If it were a regular semester. So so testing tips. So we have a few things that we can do to make our testing a little I don't want to say easier, but just a few things that we can do to organize our tests a little better. So first, we have assert true. This is your go-to. This is the sledgehammer approach. Assert true is always going to be able to do what you want it to do. You can write any Boolean expression you're capable of writing. Assert true is going to be able to handle that. So anything you can write as a Boolean expression, which is like anything, is going to work with assert true. But if there are specific situations that you're in, that say you're checking if the returned value of a method is what is a specific value, you can use something. You can use assert equals. Oh my goodness! You can use assert equals. So assert equals, as the name implies, is going to take two values and check if the two values are equal to each other. And if they're equal, the test passes. The test case passes. If they're not equal, the test case fails. So if you have the specific situation where you're asserting if the return value is one very specific value, you can use assert equals. It's just a handy thing to use. One, it's just a little easier to write, and it's going to have some benefits that we're going to see in the next set of slides too. And it gives you better feedback in Autolab. So if this test case fails, you're going to get some nice formatted feedback in Autolab that says, I expected this, but what you actually gave me was this. And it's just a little easier to debug. Whereas assert true, if assert true fails, it said, well, I expected true and I got false. So good luck with that. And then you got to go through your code to figure out what actually failed. So it gives you better feedback. But you can't always use this in cases where you can't use assert equals. Assert true is still sitting there when you expect two different correct values, the cat and dog example for best key. You can't use assert equals for that because you're not asserting that the return value equals a very specific value. That's not the situation you have. So you have to go back to your assert true. If you're getting used to assert equals, that's a situation where you got to pull out assert true again. Again, that's your sledgehammer. Assert true is your trusty assert. It's always going to be able to do what you want. Assert equals is basically assert true, do these things equal each other. But you could always rewrite an assert equals as an assert true. And then you can have hint text. So if any test cases, whether you're using assert equals or assert true, or there's all kinds of other ones, assert null, assert not null, assert false. I think assert not equals is one. I don't remember. But there's all kinds of them. And then for any one of them, you can add another argument that's a string as the first argument. And this string is going to be printed to the screen if the assert fails. So this is still asserting that result equals 5. But if the test case fails, it's going to print expected 5 on input 0 got result. It's going to print that to the screen as your hint text. That's your first hint as to what the bug might be. The big thing here, like assert equals will say expected and actual, which I have these arguments backwards. It'll say I expected this, actually gave me this, but it won't tell you the input because it doesn't have that information. This input of 0. So one very helpful thing to put in the hint text is what the input was. So on input 0, I expected this and got this. So it can be helpful to have your hint text when you're debugging. All right. I think we can get caught up. Today. The recursion. I think the recursion usually doesn't take as long as a full lecture. I think I usually have time at the end of that one. This one usually takes up the whole time. All right, so let's do a little bit of IntelliJ. Let's see what these things look like in the code. So I have my test cases that we saw in the slides. And by the way, you could always ask yourself the question, is this enough testing? Like you might still say that's not enough testing. We don't have any very large values like this. We don't have very large negative values. Like we can always add more testing until the point that we're testing every valid integer value. So at some point you do got to stop writing test cases. That's the one thing I see missing here is large positive inputs and very large magnitude negative inputs. So you could always add more. But this would be enough tests. This would certainly get you through AutoLab. If this were an assignment, this is absolutely getting you through AutoLab. Probably 3 test cases will get you through AutoLab. If you have any positive, any negative, and 0, those would be the 3 that I'd really be looking for in my AutoLab testing of your tests. Okay, but when we have this code, we're going to see all kinds of run buttons here. And it's important to hit the right one. There are a lot of them. So there's going to be a run button for every single test method. If you want to run just one individual test, then some classes have changed. Oh, because I was running the debugger. Where's my debugger? Stop the debugger. So we can run individual test methods. So I'm just running test add 5 here. It's not the one I ran. Test add 5, I ran test add 5 with negatives. If you push the button on the class, that's going to run all of them. For me, I'm always afraid that I'm going to hit the wrong run button because I have hit the wrong run button before. Eventually you make every single mistake, so you remember all the mistakes you make. So I don't like hitting the wrong button here. If I'm scrolled to here, I might think that this is the class one and think I'm running all the classes, and then for some reason I don't notice it down here that I only have one test name. It sucks. So I got in the habit of always right-clicking the class and running it this way. That's always going to run all of your tests in that class, so that I'm never going to hit the wrong run button. Sometimes I do just want to run one method, and I'll do that, but very deliberately. If I'm trying to run all the tests, I always run it here. And then once you run it once, then this button, I don't think I mentioned this last week, this button will by default run the last thing that you ran, not the current file that you're in. So if I'm over in double tests here, and I hit this run button, it's still running add tests, the last thing that I ran. So the first time you run things, definitely run it manually. And then after that, being careful, watching here, you can actually set this to current file. So then it always runs whatever file you're looking at. But a lot of times you don't want to do that. When you have a multi-file project, your main method is somewhere in a file over here, but you're working over here. So you don't always want to run the file you're looking at. Or you're editing, you're writing this code, but you want to run your tests. You're often in code that you're not actually running directly. Anyway, so that's running tests. And then if we break our method, one thing I like to do is always break my code. So if I add 6 here and then run add tests, I should see all my tests fail. And there it is, all my tests are failing. And now I know that my testing is actually doing something. I like seeing my tests fail, usually intentionally, so I know that I am actually asserting something. For example, if I forgot all my test annotations, these tests are going to pass. If I forget all my asserts, if I don't have a test with no asserts, never fails. It'll pass any code ever. And I'll often see students do that in office hours. That's not too common these days. But I'll occasionally see a student in office hours with a whole bunch of really good tests that they just never asserted. They never asserted anything. Doesn't matter what you write in these methods. If you never have any asserts, it will pass all the time. And you'll catch that if you go to your code and intentionally break it and see your tests fail, then you know that they're actually testing something and doing their job. Then I'll fix it, see them pass. Now I'm gaining confidence that my code is actually correct without having to have something like Autolab or a supervisor or a senior dev looking over my code and making sure it's correct. I'm going to be pretty confident before I even go to them. All right. So let's move on to the next content. I have this method here. Just like the add 5 method, this is a very simple, basic method. No punches pulled here. We're not going to look at longer string. We're going to do the very much simpler one. Again, so we're not bogged down with the code itself. So I have this method. It takes 2 strings and returns the concatenation of those strings separated by a space. So whatever the first parameter is, then a space, then the second parameter. Very simple method, then returns that, takes 2 strings, returns a string, combines the strings, separated by a space. Then I have these test cases here, and I want to check my code. So I have string A is hello, string B is goodbye. I expect the output to be hello space goodbye. My test case, no tricks or anything here. The test case is very straightforward. I have 2 inputs. I expect them concatenated, separated by a space. That's exactly what I have here. I don't have any typos, nothing. And I'm going to run, I am going to use the individual run buttons for this example. I'm going to run just this test case. So let's run this, which absolutely should pass, but it doesn't. I have an assertion error. This is what you see when an assert true fails. You're going to see assertion error, and it doesn't have anything to tell me. I asserted true, it failed, so it must have gotten the value false. So this equal resulted in false. Those are definitely the same string. And we can even verify this. If we look at combined strings, so if we grab this, go output. Oh. I gotta remap my control key. When we run this again, we can see what we printed to the screen. I guess I should use a hint text for that. I just showed you hint text. Let me use hint text. So we have our hint text. Our hint text is only printed to the screen. Oh, I didn't even print that to the screen. Is only printed to the screen when the test case fails. So this test case failed, and we print to the screen, hello, goodbye. Our method's doing everything it's supposed to be doing, but this test case fails. Well, shit. I'll have to think about that one. So that test case fails. So let's move on to something else. Let's do another simple one. These methods are so simple. How do we ever have a mistake in these? That's crazy. Okay. Write a method, takes a double, returns that double times 3, call it times 3. That's basically how this would be worded if it were on a programming task. I'm returning x, the input, times 3.0. Looks great. I'm happy with my code. Manually verifying this with my eyeballs. If I weren't doing any testing, I would say that method looks great. Actually, the method is great. There's nothing wrong with that method. I don't know why I worded it like that. And let's write a test for it. So I have my method. I'm going to multiply 0.1 by 3. I'm going to grab that output. I'm going to print it to the screen. Actually, let's do it as a hint text again. I do need to... Value of. It's been a while since I manually converted a primitive to a string. Good to remember the syntax there. So 0.1 multiplied by 3, grab the output, and I expect that y to be 0.3. 0.1 times 3 is going to be 0.3. Nothing wrong with my test case, right? I'm going to run this test, and the test fails. The test fails, and I can see something interesting in my hint text here, that what was returned actually wasn't 0.3. With strings, I did get the right value, so that was weird. With doubles, I actually didn't even get the right value. Like, I don't even expect this to pass, because 0.3000004 is not equal to 0.3. So I do expect this to fail. I just don't know why my code returned something that's not what it should have returned. Like, there's 0.1 times 3 did not return 0.3 exactly. So we got some thinking to do. We got to work on these. What is even happening with these? Because you would expect, unless you already know what I'm going to talk about, you would expect both of those test cases to pass. Like, it seems like there's no reason for them not to pass. But they both failed, so what the hell? Demo we just did. So let's talk about testing strings. This test failed. This failed, but why? And the TLDR of this is never ever use equal equal when you're comparing two strings. That's the big takeaway with this. Spoilers, it's going to be the same takeaway with doubles. Never use equal equal to compare two strings for equality. Never use equal equal to compare two doubles for equality. At least in Java, especially for the strings. Some languages will let you just use equal equal to compare strings and everything's fine. Not so much Java. Java doesn't like this, so this is more of a Java-centric thing. But don't use equal equal to compare two Java strings. Don't do it, don't do it, don't do it. And this will be true for any non-primitive. Don't use equal equal for any non-primitive values or doubles. So for ints, equal equal is fine. For booleans, that's about it. Really, ints. There are other types that we don't use in 116, like byte, long, short. Those types, they're all integer values with different levels of precision, different number of bytes to represent the values. But really, your integer values in Java, that's all you should be using equal equal for. You could use it for booleans, but it's rare that you have a case where you're checking if two booleans are equal to each other. Usually you're checking if it's true or false. You're not checking. Anyway, but 2 ints, that's really the only time to use this. Anything else, you're using something else to compare those two values. Often the dot equals method that we're going to see in a second. But equal equal for strings, no good. So what equal equal does is checks if the values stored in your variables are the same, right? That might sound obvious on the surface, but if we think about that a little bit, we have a problem because string is a capital S. Now we pretend string is a primitive for our memory diagrams, and most of the time we're going to get away with that just fine. This is the one exception where that does bite us a little bit. Because string starts with a capital S, that means this is actually an object on the heap, which means A and B both store references to those objects as their values. So even though we can see this is going to resolve to, we think of it as resolving to the value hello space goodbye, it does not. This string literal is not literally a string. It's not the string hello space goodbye. It is a reference to a string on the heap. So what we're doing is taking a reference to a string with the value hello goodbye and checking if that reference equals a reference to another string, which also happens to have the value hello goodbye. But these are two different strings. Since they're two different strings, the values in these two expressions resolve to, they're resolving to two different references. Those references are not equal, therefore equal equal is not going to say these are equal. Equal equal is not going to check the values of the objects that are referred to by the references. Equal equal just says, are these two references the same? Because that's what's being stored here. So whenever you have these capital letters, you know you have references to the heap. Yes, strings, we pretend that they don't. We pretend they're values, but they are actually references to the heap. Equal equal is going to get us in trouble. And what's worse with strings is that strings are weird in Java. They're immutable. I'm not going to go down that rabbit hole unless somebody wants to talk about immutability. That they do behave weird, and that sometimes these two references will refer to the same string magically. TM. And so if you start checking strings with equal equal, sometimes you will actually get away with it, is the scary part. And then eventually one day it catches up to you and you have all kinds of bugs and you have no idea why, because you didn't change anything that you were doing. But the way Java strings worked, you just happen to find a way. And this example is set up specifically in a way by calling a method that returns the two strings. If I just did string C equals A plus space plus B, then those two values are C and this string literal. Those are going to refer to the same string object on the heap magically because of the way Java strings work. They're actually going to share that object. So the fact that I called this in a method, I made sure that it was getting a new string object and that the references would be different. So sometimes you get away with it until you don't. So just don't use equal equal to compare two strings. What are we going to do instead? The dot equals method. So whenever you have to compare two strings for equality, you're not using equal equal, you're using dot equals every single time. Never use equal equal to compare strings. You could even see the warning. When I was in IntelliJ, kind of spoils the surprise, but there's a warning underlining my equal equal that says, hey, don't do that. If you're using assignment A equals B, do they have the same reference? So that A equals B? Yes. Yeah, so if I said string B equals A, then it's going to be just like we did with array list and hash map in 115. They're going to, and last week, they're going to refer to the same object, and then equal equal and dot equals will both return true in that case. So the usual way that the references work, but also strings are extra tricky because, let me just demo it. Strings are extra tricky because even without, so if we do string let me do the one from your question first. String B equals A. Assert true A equal B. This is going to pass. And let's comment this one out. Let's run this. This is going to pass because they'll refer to the same object. And we can verify this in the debugger. I got to move my mic. No, I don't have to move my mic. So this is referring to a byte array 1367. And we can verify hello 1367. They are referring to the same object. But strings are extra tricky, because even if we do string C equals A plus space plus B, string D equals hello goodbye. Get rid of our method call here. And then assert C equals D. We actually get away with this one too. We shouldn't. I almost wish we didn't, because it just builds bad habits. It reinforces bad habits. Oh no. I will. In the back of my mind, I'm like, what if this passes? Or what if this fails? I mean, well, that's good. I'm glad. Unless I have a typo here. Doesn't look like it. Oh, I don't want to spend forever on this one. But I do want to see what's going on here. So we have 1389 and 1390. I'll go back to strings are weird. I expected that one to... expected this one to pass. Maybe it's the order. If I do it in this order. Alright, well, because I want this to work, I'll do one that... This one absolutely should work. If this one doesn't work, I might just retire. This one should pass. So even though it looks like I'm assigning these to two different values, that I have two different objects. This is like saying D equals new array list, C equals new array list. Those would be different array lists on heap. But with strings, it's 1369, 1369. These are actually referring to the same object because that memory is shared. So Java likes to optimize the memory usage for strings. So it's going to say, hey, you're assigning C hello goodbye, but I already have hello goodbye on the heap. So I'm just going to refer you to that same hello goodbye as D refers to and save space. So it optimizes the storage space. I expected even with the concatenation for that to work, but it didn't. Let me give it one more try. What if we do this? Maybe it's because I had variables. Yeah, so that one passes. So even when I'm doing a concatenation, that's going to be the case. It's going to say, hey, I already have hello goodbye on the heap. And we can verify that these are referring to the same object, even though we don't really expect that to be the case. 1369, 1369. So they're referring to the same object. So strings are weird. They're just weird. Sometimes you get away with it, sometimes you don't. What if I do a hybrid approach? Okay, and then that fails again. So sometimes you get away with it, sometimes you don't. And it's even weirder than I thought. But always use dot equals. In all of those situations, every test case we just did, if the values are the same, dot equals will actually follow the references to the values and check character for character, are all the characters the same value in these strings. And then if you have strings with the same value, it's going to pass. So is it worth finishing that conversation? Probably. So this test fails, even though the values are the same, but the values of the variables are not, because the values of the variables are references. But now we use dot equals. That's going to check the values of the strings themselves, and this will always work the way you expect it to. I'll never be wondering why a test case failed on this one, because, well, if it fails, it means the strings weren't actually the same values. The values of the strings themselves, not the values, oh my goodness, not the values of what did I even do there? Not the values of the references. Okay, so now this passes and everything's good in the world again. And this is another case where assert equals is going to be a bit nicer for us. What assert equals will do is call dot equals on the values. So, excuse me, if I have assert equals in the two strings that I want to compare, I don't have to worry about equal versus dot equals or anything. Assert equals is always going to call dot equals, so it can save you a little bit of time. This doesn't always work for you. Again, best key that's exposing this, if you're getting too used to assert equals, best key is checking strings. So that's another way where I'm forcing you to remember, hey, use dot equals with your strings, because you have to do it manually in an assert true. It's all designed, that method's designed to get you to think about a lot of these things. So assert equals will do it for you when you can, when you're looking for one specific value, but sometimes you do have to do your dot equals manually when you're expecting either cat or dog, for example. Okay, so let's look at a little example. We're going to add this plus minus to our previous example, and our letter grades, we want to get pluses and minuses, not just grades. So let's get at least one non-toy example. We have a lot of really simple examples in this lecture, so let's get one with a little bit more going on. We're going to call this method letter. This was our testing. Last time we saw the letter method, we just had a main method, we gave it 3 inputs, and we asserted the outputs. A very weak test because we're missing a lot of expected outputs. B and D are never tested. A lot wrong with this, but that's the way we did our testing last week. And now we want another method that's going to return pluses and minuses. So we give it a score. It's going to check the ones digit. We're going to use modulo 10 to get just the ones digit. We're going to check if that digit is greater than or equal to 7. So if it's 7, 8, or 9, give it a plus. If it's greater than 2, but this assertion failed, so if it's 3, 4, 5, or 6, there's no modifier. And otherwise, it should be a 0 or 0, 1, or 2. We're going to give it a minus. So that's going to give us our grades in this kind of format for all A, B, C, D, and F, which is one of our bugs here. And this code has quite a few, I shouldn't say quite a few, but has several bugs in it. We will, time permitting, we might revisit this one. I don't know if that's going to get cut for the summer to make everything fit, but we might revisit this one. I think this does get cut because we have the midterm that day. I don't think I'll get to it. But there is one more bug, like you can have F pluses and F minuses. So the plus minus should check if the score is greater than 60 as well. If it's less than 60, just return empty string. That's another bug that we have. It's an intentional bug, so we can talk about more testing. Because this, at a glance, all this stuff looks right, but once we write our unit testing, we start to realize things go wrong pretty quick. So let's test this method. We have 3 test cases. Let's use the same inputs that we used for letter. That's fine. That's a start. Definitely not enough testing. We need, I'd want to see 10, 20 test cases for this one to really test everything. I want to test every boundary between every letter grade, every plus, minus, and just make sure everybody's getting the grade they want. And hell, with a test like this, with something like this, you could exhaustively test every valid grade from 0 to 100, and then have some invalid inputs too. We don't even handle invalid inputs in this code. So that's another edge case that we would get, which is a topic that I bring up in the next time this comes up, which we might not get to. Checking to make sure score is less than or equal to 100 and greater than or equal to 0. Same with plus minus. Making sure it's a valid input as well. A lot of stuff to talk about with this one, so I'll just glance over it here, but just know that those are things that this example is motivating for future conversations that we might not get to, so I want to mention them here, at least to get them out there. But a lot of things wrong. Invalid inputs, plus minus on F grades, giving F pluses and F minuses, which aren't real grades. And one other one, but that's the one that we're talking about today. So this is a good start. We're going to call our method on these three inputs with 95. I expect no plus or minus, and I'm going to have my hint text here. In PM, where I'm capturing the output, should be empty string, so I'm going to assert that it equals the empty string. I'm using assert equals, so I don't have to worry about dot equals for my strings. And assert equals is going to call, I think I said that, right? Assert equals is going to call dot equals. There's no real magic here. Assert equals says assert true PM dot equals empty string. 78, I expect that to be a plus, and 51, I expect that to be a minus, even though it's an F minus. It's weird, but our code, our plus minus method itself, should return minus on 51. And our code passes, so we're feeling good. Hey, we wrote some test cases and it passed at our test. That doesn't mean a whole lot. A lot of, it is tempting to get excited as soon as you write some test cases and it passes, and it is a big step. But there can be a lot wrong still. We just went over a bunch of stuff that's wrong with this code. And then we're like, you know what? We need some more test cases. I heard Jesse talk about edge cases, and in this case, 100 is one of our edge cases. 0 and 100 would be our edge cases for this code. Those are two inputs that should be handled a little differently. 0 not so much, but 100 for sure. So we write our test case for 100, and that student better be getting their A+. They perfected the course, and they demand perfection with our testing. We better be giving them the right score. But they don't. They get an A-. That student will be upset. This will be an immediate email as soon as grades are released. They're going to be upset, and rightfully so. So what happened? We can trace through the code, and this will be what we do with the debugger. We're going to get this output, should be plus, but got minus because that's our hint text, our hint string. And then we're also going to get this output when you run assert equals. When assert equals fails, it's going to give you this output as well. And even the expected, I don't know how I messed up these slides. The expected and actual are backwards. The code's backwards. This should be plus then PM. Even in the text, and then every semester I say I'll fix it, and then I forget about it until the next semester. I just gotta go through all my slides and tune everything up. But anyway, we expected plus and actually got minus. And we can step through our code. We would run the debugger at this point and say 100 modulo 10. That's going to take just the ones digit, which is a 0, which is going to hit our else, which is going to be a minus. So we have a bug here. And we passed 3 of the tests, so we should be feeling good. But we failed the 4th one. And, every class ever has taught you, hey, that's a 75. It's still passing. You're okay. That's great. No, not in programming. We need to pass every single one of those tests. We need to release bug-free code. Once a test fails, the job of a test is to expose a potential bug. If a test fails, that means that it did its job in exposing that bug. So we know we have a bug. The next job is to fix it. We need to eradicate that bug. If we just say, yeah, I know we have a bug, but I'm okay with that. Let's just release the code anyway and let this perfect student get an A-. We don't do that. Like, you should be pretty mad if I did that with grades. If I'm just like, yeah, I know my code to generate your final grade is buggy, but whatever. hey, I got it right for most of y'all. Isn't that good enough? Well, if you're one of the ones that got the wrong grade, unless it goes up, nobody's going to complain if they get a better grade, you're going to be pretty mad, and rightfully so. We demand perfection in computer science, in programming. We should demand perfection everywhere, right? So we expose the bug, we need to eradicate it. So now that we know that our test case fails, what I like to do is set a breakpoint right here and then use the debugger. I don't have time for a debugger tutorial today. Step through the code and then see where it goes wrong. And we did step through the code. I kind of simulated that. And then we found the bug. The next step is eradicating it. And this edge case doesn't really fit the logic of our program. We're not going to be able to take the ones digit and just work off of the ones digit with this one. So we're going to have a special case, a special if statement for our edge case that says, hey, handle the score of 100 differently. 100 just doesn't fit the mold. Just return plus if you see the input 100. Now we pass our test cases. Our 4 are pretty weak testing in this case. One of them gives an F- even. That's kind of a bad test case. And now we're passing those 4 tests though, at least. This is usually where I say we'll visit this one later and fix the rest of the bugs in a future lecture, but I don't think we're getting there in the summer. Okay, let's move on. I'm looking at the clock. We gotta pick up the pace a little bit here. So this test also failed, and we gotta talk about why this one failed too. And there's a lot to talk about with this one, so let's do it. So we just times this by 3, and we didn't get what we wanted. And the TLDR is don't use equal equal, but there's a little more to it than strings. Strings is just don't use equal equal, use dot equals instead, or assert equals. With doubles, we got more to talk about because we saw this really weird behavior. These values actually were not equal. Even if we're using a dot equals, it's not like it should return true because these values are different. If I'm checking if 2 things are equal and they're not actually equal, I want my dot equals to return false. So the bigger question is, why didn't we get the right answer here? And what are we going to do about it? So with doubles, we got to talk a little bit about how doubles are represented in the computer and how binary works. So with doubles, we have a 64-bit representation for the double. So whatever can fit in 64 bits, that's how we're going to represent our doubles. And it's like this. You're going to talk a lot more about this format in CSE116. So I'll keep it brief here. Is you have a 52-bit fraction portion, and then an 11-bit exponent and a sign. And this is basically scientific notation. So this value is 1 point the fraction times 2 to the exponent. So just like you have scientific notation in base 10, this is scientific notation in base 2. And when you have that, when you have a decimal in base 2, say I have the decimal 0.11, I'm going to assume, I don't know if this is a safe assumption, but assume you know a little binary. I guess I can very briefly go over it. With binary, it's just like base 10 where you have like the ones digit, the tens digit, the hundreds, thousandths. With binary, you have the ones digit, the twos digit, the fours digit, the eights digit, the 16s digit. So it's instead of multiplying by 10 each time, you multiply by 2. And the same thing happens on the other side of the decimal, which you probably haven't seen before, is on the other side of the decimal, in base 10, you would have the tenths digit, the hundredths digit, the thousandths digit. In base 2, in binary, you have the 1/2 digit, the 1/4 digit, the 1/8 digit, the 1/16 digit. So the 0.11 is 1/2 plus 1/4. So this is how we represent 3/4 in base 2 in decimal, in binary. So in decimal, in base 10, there are certain values that we cannot represent as a decimal. For example, 1/3 is one of those values. 1/3, no matter how many 3's we write, is not equal to 0.33333333. Eventually, we're going to stop writing 3's either because we ran out of patience or we ran out of paper, or if we're on a computer, we just ran out of hard drive space. We can't represent 1/3 exactly as a decimal, because this repeats out to infinity. We would write the line over our threes like we do in grade school, but there's no actual way to do that in the computer, at least the way we represent values that we saw in the previous slide. Because in doubles, if we want to represent a value as the sum of powered fractions of 2, we can't always do that. In 0.1, which was a careful, deliberate choice in the example, 0.1 is one of these cases where we can't represent it exactly in base 2. We can represent this in base 10 easy enough, but just like 1/3 can't be represented in base 10, 0.1 cannot be represented in base 2. This is 0.000110011, and that repeats forever. So at some point we have to just stop writing 0011 and truncate the value. So we're going to store not exactly 0.1 in memory, but something like 0.1. So we have 1 point, and then this will be the fraction part of the decimal, and then it'll be raised to the 1, 2, 3, 4, the -4 exponent. So that'll be how this is represented as a double. But the important thing to note is that this needs infinite digits to represent it exactly. And we have a finite number of digits. We have 64 bits total, 52 of those for the mantissa, or the fraction portion. So we cannot represent this exactly in a double. So when we have 0.1 stored in a 64-bit IEEE double, that's the IEEE standardized how doubles work. So this works in any language. They all work the same way. They're all representing doubles in this same structure, the same format. So any programming language, you go to Python and do 0.1 times 3, you're going to get the same thing. C++, it doesn't matter. You're going to get the same thing, except JavaScript, because JavaScript's weird. But you're going to get this truncation because 0.1 can't be represented as a double. So we have to truncate. So when we have 0.1, this isn't actually 0.1. It's something very close to 0.1, but it is not actually 0.1. In fact, when we print 0.1 to the screen, we do get just 0.1 printed to the screen. So it pretends that it is 0.1. But once we start doing some math and do some operations on 0.1, that what we call truncation error, because we had to truncate the value and erase some of our value, which means we lost some precision. Once we start doing math with that truncation error can compound and start affecting our code. And specifically, when we take 0.1 and times it by 3, we don't get 0.3 because we didn't start with 0.1. So that's why we're getting this little bit of a difference, this very slightly off value that's basically 0.3, but it's not exactly 0.3. So we can't say, does it equal 0.3? Because, it doesn't. But this is often going to come up. When we have doubles, if we're using equal for the doubles, these truncation errors are constantly going to mess us up, and they're going to give us the wrong values. So in our test cases, of course, we have to handle this some way because we're constantly checking if doubles are the right double. We're checking if it returned the right value. But also, in your code, if you have, like, if this double equals this double, then do this. If you're checking doubles for equality in an if statement, you're also going to come across the same issue. So we need some way to handle this. And the short answer is never use equal to compare doubles. Okay, if we're not using equal, then what do we do? What's our alternative? And we're going to check not if doubles are equal, but we're going to say if they're close enough, we're going to consider them equal. So how we do this is we're going to check if the difference, the absolute value of the difference of the values, this gives us the magnitude of the difference, is less than some small value, then we're going to say they're close enough. And we're going to be careful of how we choose. I call this epsilon. I steal that from math. Actually, a few things I got to talk about in this slide, don't I? I steal this from math, the naming convention. If you have a small value in math class, they usually call it epsilon, so I stole that. And this is going to be... Oh, I don't want to talk about all this stuff today. What was our time? No, I can't talk about all this. But this is a private variable, meaning it's local to this class. It's final, meaning it's a constant. It's a double. We've seen that before. And when you have a constant, the naming convention says spell it with all capital letters. And I'm going to set it to some value that's meaningful to my situation. For 116, 0.001 is fine. But if you have specific situations, like you're asserting that the distance between atoms is correct, you probably want a much, much smaller epsilon. If you're checking if the distance between cities or planets is correct, you probably want a much larger epsilon. You're going to tolerate a lot more error. But 0.001, that'll be fine for 116. If you just use this all the time in 116, that's fine. Don't make epsilon too small, because then the truncation errors are going to start interrupting your logic. If epsilon is lower than a truncation error, it's not going to work for you anymore, because it's not doing its job of ignoring truncation errors. And make sure you take the absolute value. Probably once a semester I see somebody who copies and pastes this a whole bunch of times instead of just calling it as a helper method like I have set up here. Oh yeah, that's the other thing. This is a helper method in a test class. So notice that I do not have my test annotation up here, because this itself is not a test. I'm just using this helper method in my actual tests. But make sure you don't forget the absolute value. Once a semester, somebody will copy and paste and forget the absolute value, and not understand why they were copying and pasting that, because they didn't take this lesson to heart, or maybe they just forgot and didn't notice. I don't know. It's hard to believe that. But don't just take the difference, take the absolute value of the difference. The difference itself might be two values that are completely different and have this very large magnitude negative value, which is less than 0.001. So the test is going to pass, even though your code is completely incorrect. So make sure you take the absolute value. Don't forget that. Or you can use assert equals. Assert equals to the rescue again. Assert equals for doubles can take a third argument, which is going to be your epsilon from the previous slide. This is your tolerance, your allowable tolerance. It's saying check if these two doubles are within 0.001 of each other, using the exact same logic we just saw on the previous slide. So in your test cases, you can use assert equals for doubles and then give it your tolerance. But you can't always do this. For example, if you have a conditional where you want to say if these two doubles are close enough to each other, then do this code, then you're going to have to manually do something like this. Take the absolute value of the difference and check if it's less than some small value. So you do have to do this sometimes. To be honest, I don't think I have a setup in the assignments that forces you to do that in 116, but eventually in your career you will have to compare doubles manually to make sure you know how to do that without using equal and getting truncation errored. Okay, let's roll right into it. Half an hour for recursion. We got this. Before we talk about recursion, just another side note, just like the memory discussion on the in the previous lecture. Let's talk about interpretation versus compilation, because you're going to start feeling the difference between these two. If you haven't already, you probably have already. Interpretation versus compilation. So let's explain what's happening with that. So in code that's interpreted, you write code. If it's interpreted, that means there's a program that's reading your code line by line and executing each line one at a time. Just execute line 1, execute line 2, execute line 3, etc. Compilation is a different beast. This is where instead of your code just being ran directly, your code is never actually ran. What happens is another program called a compiler is going to read through your entire program and translate it into another language, and then there's another program, there's an interpreter for that other language that actually runs that translated code. So there's an extra step in the process that checks all of your code first before executing anything. The reason we're talking about this is Python from 115 was an interpreted language, meaning Python ran line 1, ran line 2, etc. The effect that this has on you, the practical effect of this is, one, your Python code is going to run immediately. You hit the go button and it goes. There's no delay there. It just runs, like real snappy, really just goes. But there's no checks beforehand, so it's common that if you have an error, it's going to be a runtime. I forgot I can't highlight. It's going to be a runtime error. So your program's going to run, and then if it hits a line with a bug in it, it'll crash while it's running, which is, you can have difference of opinions on this in the next type of error we'll talk about. But for one, I don't like this kind of error. These are scary because you don't know that you have an error until you run your program, which can get frustrating. As opposed to compilation, so Java is a compiled language. So from 115 to 116, there's a lot of changes, but you're switching from an interpreted language to a compiled language. So if you have errors in your Java code, they're going to be compiler errors most of the time. You can still have runtime errors, but you're going to have compiler errors, which means when the compiler is translating your code to that other language, it runs into an issue where your types don't match, or you're missing some syntax. There's just something wrong. The compiler is going to say, hey, I was looking at your code, I was translating and everything, and I came to a spot where things just didn't look right. I didn't know what to do. I just thought I'd let you know so you can fix your bugs. So the compiler really has our back with this, where it's looking over everything and making sure we don't run our code with errors. Because it's checking everything for us before that ever happens. So it flags us down right away. Hey, you got an issue here? Let's fix this and then run the code. So it's very hard to run buggy code. You can run incorrect code that doesn't do the right thing, sure. But it's hard to write actual buggy code that crashes in Java because that compiler isn't going to let you get that far with any obvious bugs. Where Python, you can have type mismatches and all kinds of crazy crap going on, and you're not going to know until you run that specific line of code. And if you have a bug in like an else statement, and in your testing you only hit the if statement in Python, you can have programs crashing when your users are using it, which is very scary. Java isn't going to let you do that. But the other side of that is when you hit the go button in IntelliJ, your program doesn't run immediately. And that's not just an IntelliJ thing. It's not just a Java thing. That's a compiler thing. So when you hit the go button, you'll notice a progress bar on the bottom of IntelliJ. That progress bar is the compiler compiling your code, translating all your code before it can run. So if you run your code, it takes a little bit to compile. But if you just hit the run button again after that, it doesn't have to compile again if you didn't make any changes. So it will run immediately the second time. Usually we're going to make changes before running it again anyway. But that's why it seems a little laggy when you run compared to Python. It's because of the compilation step. And your code is translated into a language called Java bytecode. This is what our Java code is translated into, and then the Java bytecode is executed by a program called the JVM, the Java Virtual Machine, or just Java. If you've ever seen these pop-ups, which I think are pretty rare these days, I think it just updates in the background without telling us anymore. We used to have to update them manually. But if you've ever seen one of these, this is your JVM that's updating when Java updates. And the JVM is installed on, as they always like to brag, billions of devices. Do I even have it on? I don't even have it on here. But they like to brag that they're installed on billions of devices, usually right on the installers and everywhere. But it is installed on billions of devices. Pretty much any device you have is, except iPhones, because Apple has to actually do iPhones. I'm not 100% sure. Maybe iPhones have a JVM. I know Android does because Androids are Java based. But your desktops, your laptops, they all have a JVM on them. They all have Java installed. So your Java bytecode can be executed on any device that has a JVM, which is most of them, most any device you're going to find. All right, so that's compilation. That's a very brief discussion of compilation. There's a lot more we could talk about with it, but I just wanted to point out some of the differences from switching from Python to Java. A lot of the differences you feel are because Java is compiled. And the fact that Java is strongly typed, you can only have a strongly typed language if you have a compiler, something looking over all your code to check the types. Because the types don't matter at runtime. When your code's running, it doesn't matter when it's being interpreted. The types are, types matter, but you can't, like, the type annotations don't matter because at runtime, your types are either right or they're wrong. If they're wrong, your program crashes. If they're right, your program runs. But the fact that we specify all our types, that's so the compiler can check our types for us. So the strong typing is enabled by the compiler. Okay, now on to recursion. We got this. 25 minutes, we can do this. We might not get through the entire memory diagram, but we'll get the idea of recursion out there. So with recursion, what recursion is a method or function. This applies to functions as well. I don't mention functions often in this semester because we don't have them in Java. But this is a method that calls itself. That's the whole definition. That's what recursion is. The implications of this and wrapping your head around what's actually happening takes a while, but that's the whole definition, is a method that calls itself. If a method calls itself, it's a recursive method. If it doesn't call itself, it's not a recursive method. That's it. End of story. So the implications of this we want to talk about, and I'll do it through a memory diagram. But we have here a method that adds two ints together. Yes, it's another simple to understand method in the sense that I know that this is supposed to return the sum of a plus b, but now the implementation is much more confusing. We know what this is supposed to do, and I'll say, trust me, bro, it does do what it's supposed to do. It will add a plus b and return that result, but the implementation is crazy. It's way overcomplicated. Obviously, you would just say return a plus b, or not even write this method at all. You just say result equals 4 plus 3. But then you might just say, well, the whole program could be print line 7. But anyway, we're here to talk about recursion, so we overcomplicated the crap out of it. So a plus b, we're going to evaluate with this chunk of code. We're going to break it into 3 cases. B equals 0, B is positive, B is negative. And we're not going to see that B is negative in this example because B is, in fact, positive for this example. So we're writing a method named add. We have to add a plus b. And in the definition of this method, we're calling a method named add. And these are the same method. This is a method that calls itself. This is a recursive method. They are the same method. So let's see how this works with a memory diagram. So let's go, again, as usual, I have the memory diagram in the slides, but I want to do it live. I know my eyes just weren't seeing it. I'm like, I know it's in this package. So let's grab this code. Let's head over to our tracing tool. Let's trash can this, hide the tool. Oops, show the toolbar. We are in Java. Let's hide the toolbar. Let's select this, paste this, get rid of all the examples that we're not using. Add, not using factorial. No, that's the zoom level I want. Okay, so let's do this. We know it's going to print 7 to the screen. We all know that. But we're not going to think ahead and everything. We're going to do this one step at a time. You know what? I feel confident we can do this in 22 minutes. So we have our main stack frame. Every Java program starts with one. We have result. And I'm going to start, even without a time crunch, I'm going to start blowing through the things that we've covered a bunch of times. We did our 115 review. You know what stack frames are, return values, variables on the stack. We should all be beyond that by now. Parameters inside our method calls, A getting the value 3, B getting the value 4. We're beyond all that. If there are questions, I'll be happy to field them. But I'm assuming that we're all real good on all that stuff. You've had a whole semester in 115. If you're a transfer student, you had to learn it a lot faster if you didn't take 115 at UB. Or if you're not even a UB student. I guess in the summer you don't even have to be a UB student. But you had to learn it quicker in those cases. So if you still have questions, if it's still fuzzy, let me know. But I'm going to start blowing through it a lot faster. Okay, so we called add, and we're ready for the first line. And we're going to check if b equals 0, b is not equal to 0. We don't need... There's a way to get rid of the heat, but I forget how to do it. Oh, yeah, there it is. It just didn't come up the first time. This. I think I will zoom in. We can go bigger today. And full screen. The heap is still there. All it does is resize. I see. Okay, so b is not equal to 0, so we're going to check the else if. B greater than 0, 4 greater than 0. That's true. So we're going to run this line right here, which is our first recursive call. We're going to make a recursive call to the method that's currently executing. That's crazy. You can't do that, right? How is that going to work? So here's my trick. Here's my tip, trick, whatever, for recursion, for tracing recursion at least. Writing recursive methods is a whole nother beast. That gets a little trickier. We're going to do a few not too difficult ones in 116, but they're still going to be tricky because recursion is tricky to write. Tracing recursion, here's my trick for tracing recursion, is don't even think about it. Don't even worry that it's a recursive method. Like, who cares? Don't think of this as a recursive method call. Just think of it as a method call. You were running a method, you reached a method call. We're going to do the thing we always do. We're going to put that method call on the stack. We're going to put its parameters in that stack. Those parameters are going to be assigned these values. These values have to be executed in the stack frame where, like this new stack frame, we're setting it up, but it doesn't actually exist yet. We resolve the arguments inside the previous stack frame, which is this one. So A is 3 plus 1, gets the value 4. And B is 4 minus 1, gets the value 3. Oh, I meant to switch these parameters because... No, I'm not changing it now. Just because it takes a while to trace through them all. And then we execute the method. So we start over at the top of the method and start tracing through this new method call. So we have two method calls on the stack. I am not returning this into any variable, so I'm not worrying about a return arrow. Some people like to do their return arrows back to the original variable if it's just return, everything's just returning. I'm going to skip my return arrows, which I guess is technically the correct thing to do since, since me and the other instructors get to make up what the correct thing to do is, and that's what we decided. But it doesn't matter. It's not one of the things that's ever going to affect your grade. Whatever you think more clearly represents what's happening, I'd be fine with. When we used to do these on paper, we had special notation, but we said, forget that. We're not going to bother with the tracing tool. It's just a lot of extra complexity for pretty much no gain, so we didn't bother. On a quiz, I'd probably store this value in a variable, so then it's clear what you're supposed to do. You have to return it into that variable. Okay, so this stack frame is on the stack. If b equals 0, that's false. B is positive, so we're going to execute this, and we get right to another recursive call. We have add a plus 1, which is 5, and b minus 1, which is 2. And notice that I have multiple stack frames, all with an a and a b in them. And that's perfectly fine. Our stack frames are completely isolated environments, so we're allowed to reuse variables. And before, I'm like, well, ain't that nice? We don't have to worry about what variables are declared inside other methods, which is nice. It's a really nice thing. We don't muddy up the global namespace. But beyond that, you could, if that were not the case, if you couldn't reuse variables, recursion could not exist. You can't have a recursive method if stack frames are not isolated environments. Because as soon as we got to the second stack frame here, it'd say, oh, duplicate declaration of A and B. We can't do that. Not allowed. And then everything crashes and burns. But since everything's an isolated environment in each stack frame, it's no big deal. No worries. Okay, so B is not 0. B is positive. Do it again. Add. A is now 6. B is now 1. B is not 0, so we do it again. Add. A. B. A is now 7, and B is now 0. And now we get to the interesting part where finally B is 0. So with recursion, it's a method that calls itself. If a method calls itself every single time, this goes infinite. The method calls itself, which calls itself, which calls itself, which calls itself, which calls itself, etc., etc., etc. It's going to keep going forever if the method always calls itself, because each stack frame is going to add another stack frame. Something has to end the cycle and stop adding new stack frames to the stack. And what ends that cycle is what we call our base case. Every recursive method is going to have some situation where when it's executed, it does not call itself. Because if it always calls itself, it's infinite. It has to have a situation, a condition, where it does not call itself. So every recursive method, unless you use fancy syntax and stuff, is going to have some conditional which says if some condition, don't call yourself. Just return something without going crazy with the stack. So, and for our situation here, the base case is B equals 0. When B equals 0, we hit our base case and just return A. So this stack frame is just returning A, which is 7. And the way this is set up, we have quite a bit of invisible stuff going on. But this stack frame returns the value 7. It resolves to the value 7. So now we have to go to our previous stack frames and figure out what they're going to do. So this stack frame returned. It returns execution to the next stack frame on the stack, which is this one here. And this stack frame was waiting for this method call right here. It happened to be a recursive method call, but it behaves just like any other method call. It was waiting for this method call to resolve. This method call resolved to 7, and it's going to return that value. So this is going to return 7 back to this stack frame, which was waiting for this method call to return. That returns 7. So this method is going to return 7. This stack frame is removed from the stack. This stack frame gets control again. It was waiting for this method call right here. Same thing with the other stack frames. This resolved to 7, so it's going to return 7. So this method returns 7 to this stack frame, which was waiting right here, which this resolved to 7. So this stack frame also returns 7, and this stack frame has a return error, returns to a variable, and we get result equals 7, which is in fact the sum of 3 plus 4, which we then print to the screen and end the program. So for our stack traces for recursion, just trace it how you would any other method calls. Yeah, we have a whole bunch of stack frames all called add. So, and you do have to keep track of what each stack frame is doing. So when it gets control back, remember where it was. If it was at this method call or this method call, you have to know where it was so it can pick up its execution. And then the end result, especially when we're writing recursive methods, what we have here is a method with a base case. This is always some trivial input-output behavior. On the input 0, if I'm adding something to 0, I'm just going to return that something. If I'm adding 0 to A, there's nothing to do. And if we don't hit the base case, we're hitting a recursive step that's going to recursively call the method. And we have one for positive and one for negative. I'm kind of ignoring the negative one here, but I just want the method to be able to work for negative numbers. So let's focus on the positive one. If b is positive, we want to make sure we're getting closer to this base case, because eventually we have to hit this base case or else our program blows up. We have to hit the base case. So if b is positive, I'm going to make a recursive call where I decrement b. If I call this method with b minus 1, whatever b is, I know it's positive, so if I subtract 1 from it, it is getting closer to 0. So I'm getting closer to my base case, and if I subtract 1 from b and add 1 from a, I'm going to get the same summation, the same result. So 3 plus 4 is the same as 4 plus 3, which is the same as 5 plus 2, which is the same as 6 plus 1, which is the same as 7 plus 0. So the sum of these values, the plus 1 and minus 1, will cancel out, and I'm still adding a plus b, but I'm getting closer to my base case. And I'll eventually reach my base case and return, and then all these recursive steps can return. And with the recursive step, the real benefit of writing a recursive method, in my opinion at least, is that the recursive step only has to do a little bit of work. As long as it's getting closer to the base case, it really doesn't have to do much. It's getting closer to the base case and not breaking logic. Like add of a plus 1, b minus 1 is still the same thing, but getting closer to the base case. That's all we have to do, is a little bit of work. So each stack frame is only accounting for 1. We're incrementing a and decrementing b until b is 0, and at that point a is a plus b. So we're only adding 1 each time until we've added 1 to a b number of times in the final stack frame. And then the final stack frame's job is just to return back up all the stack frames. Same with negative. I'll point this out just a little, briefly here. If b is negative, we need to increment b to get it closer to 0. So we're going to add 1 to b, and then to balance the equation, we're going to subtract 1 from a. So we're going to subtract 1 from a, negative b number of times, I guess it would be negative b, the magnitude of b number of times, and then we're going to get the summation of that result as well. IntelliJ. If we run this, we can verify it print 7. Oops, I have all my other stuff here. Let me just delete this stuff. We're not gonna. I've never gone over those examples in lecture, but just having them in the repo so you have more examples is a nice to have. So let's print 7 to the screen. If I want to add 3 and negative 4, it's going to work too. But what happens if we don't reach our base case? So what happens if instead of, maybe we mess this up. Instead of b equals 0, let's do b equals 10. So b starts at 4 and is going to decrement. It's never going to reach 10. Technically it would, technically it won't, depending on how technical you want to get. But let's run this and see what happens. And what we get is our first stack overflow error. When you get an error, whenever your program crashes, you'll get your stack trace. You should be used to these from 115. But we can see what our program was doing at the time. And what this will do is give you the entire stack. So we had a method called add on the stack that was on line 11. We had a call to add on the stack that was on line 9, a call to add on the stack that was on line 11. And we can click on these to see what was going on. It looks like we get to b equals 0 and then just bounce back and forth between these two recursive calls. So we have a whole bunch of recursive calls on the stack at this time. So if we set our breakpoint, let me set it here. I think that's the most interesting. And take a look at what's happening during this execution. Is we can see all of the frames on the stack. So we have these frames on the stack at this point. So the debugger is going to pause the first time it hits the breakpoint. So the first time it hits this breakpoint, we have all these calls of add on the stack. One with A equals 3, B equals 4. One with A equals 4, B equals 3. One with A equals 5, B equals 2. One with A equals 6, B equals 1. And then the one we're currently on, A equals 7, B equals 0. So now when B equals 0, we're going to get into this negative condition. And then we can start stepping through our code. If we take a step forward, we're going to get a new stack frame where A is 6 and B is 1, because A was subtracted by 1, B was incremented by 1. And we're not hitting our base case here. Actually, let me... and we're going to keep bouncing between these two. And we're going to keep getting new stack frames and bouncing between 6 and 1 and 7 and 0. Let me modify this a little bit. Oops, I didn't mean to do that. It's maybe a little more interesting this way. Let's just focus on the positive. Run this in the debugger again. Instead of bouncing between positive and negative. Here we're going to get B going more and more negative as we move forward. Let me hit this button, it'll be faster. B will get more and more negative, and we never hit the base case, so we just keep adding stacks, adding stack frames, adding stack frames, adding stack frames. And if we do run this, well, we already saw the Stack Overflow, that'll be the same. But then, what was our time? Oh, shit, we got tons of time. So let's do this one more time. Let's get back to our original method. And instead of adding 3 and 4, let me add 3 and 1,000. So the question I want to ask right now is, when we went infinite, we were putting infinite stack frames on the stack, and we eventually ran out of stack space, and that's what our stack overflow error is. It means that chunk of memory that we got from the operating system when we started our program, we used it all up, and we were trying to put another stack frame on the stack that we didn't have room for, and the OS said, hey, you used up all your space, you can't do that. The program has to crash because it has no other option. It's trying to execute your code, but your code needs more stack space than it had. So my next question is, how much stack space do we have? So can I put 1,000 frames on the stack? And the answer is, yeah, that just computed the right answer. So let's run that. I'm going to set a breakpoint at the base case and run the debugger. And we can see, we run the debugger, computer handles us 1,000 stack frames just fine. We got 1,000 frames on the stack. We can take a peek at any one of these and see what the values of A and B are. A is just going to keep getting incremented until B is 0, where B is starting off at 1,000, and everything's actually just fine. 1,000. It's a lot. Now each stack frame in this example only has 2 ints. It doesn't need that much room, but just to emphasize that the stack is pretty dang big. Let's try 5,000. I always forget when this blows up. It's past 5,000 though. Let's try 20,000. Okay, 20,000 was too far. Let's try 10,000. So even 10,000 stack frames, so 20,000 ints in stack frames, plus any overhead that each stack frame needs, can fit on the stack. So we have a good amount of memory here. It's not like we're really restricted. The only time you're really going to run out of stack space is if you're going infinite. If you're trying to ask for infinite space, then it's always going to blow up. But under standard operation, like how many times are you putting 10,000 frames on the stack? You have methods, calling methods, calling methods, calling methods. Like you can have 1,000 chained method calls and still be fine, assuming they have not too much stuff in them. Let's try to go to 15,000. We use some binary search and find our limit here. 15,000 is fine. Just does it just fine. 17.5. 17.5 was too much. I'm not going to do literal binary search because the math is going to hurt my brain. But somewhere in here, I'll stop here, but somewhere around 16,800 stack frames in this example, and we're fine. By the way, if we add int C, we won't have it do anything, but we'll just add another, just a dummy value. Before when, before when 16,800 was fine, now it's not going to be fine because we're asking for more space for each frame. Oh, damn it. Okay, apparently I don't know how computers work. I fully expected that to break. And it broke. Wait, what did I do wrong there? I don't know what I did wrong the first time. Oh, 10,000 should be too low. Should be 12,000 should break. No, because of the overhead. 14,000. Oh, just break for me. And then if we get rid of C again, I'm really perplexed why that worked the first time. I should have asked for maybe it's optimizing memory in a way I'm not expecting. This shouldn't have been as close as it was. But the amount of space per stack frame does matter is the point I'm making there. And we are out of time at that point. So make sure you're getting in your task 1. Expected deadline is on Thursday. Make sure you're getting in Thursday morning Eastern Standard Time anyway. So you have tomorrow, basically today and tomorrow, to work on it. Make sure you get it in. Like I said, a lot of you have already done it, so I ain't sweating it. But those of you who haven't even started it yet, make sure you're getting it done. You have everything for task 1 right now, obviously. You have everything you need. And yeah, was there anything else I want to say? I didn't make it too explicit. All right. No, it's right here. Super briefly, I did forget to make this explicit. The testing of strings where we have, but I mentioned this last time, but modulo 10 and divided by 10, those are your hints for that sum of digits. If you take the input, modulo 10 is going to give you the ones digit, start accumulating that, divide by 10 to erase that ones digit. Now the new ones digit is the old tens digit. Get that digit, add it to your accumulator, divide by 10, keep doing that process. This is why this example is in here, is to show you how to do that. Give you your hint for that one. All right, that's it for me for today. Well, I'll be back in half an hour, but that's it for this lecture. We'll be back Thursday for the big classes and objects lecture, all that stuff I say. We'll get to it next Thursday. It's all coming already in 2 days. It's coming. All right, take care, everyone. See ya.